In a separate video, the TurboTrain project in Canada was introduced, and a similar attempt to speed up using the same vehicle began in the United States. In the 1960s, the rapid development of highways in the United States led to a rapid decline in railway passenger transport. The TurboTrain was developed with the goal of restoring railway passenger transport through high-speed railways, incorporating innovative designs. United Aircraft Corporation, which primarily operates in the aviation sector, designed the TurboTrain, surpassing the conventional wisdom of traditional railway vehicles. To achieve extremely lightweight vehicles, aviation gas turbines were adopted for the drive system. Prioritizing weight reduction, only the minimum necessary silencers were used. While silencers were installed on the intake side, the exhaust side had a bold structure that discharged directly without passing through silencers. From the prototype stage, the noise outside the vehicle exceeded expectations and became a problem. Particularly, the increase of 15 decibel in noise when the engine output shaft was stopped or during ultra-low-speed rotation, as seen with Kiha 391, made the high noise during departure a challenge. However, this was a short-term phenomenon occurring only at departure, so no special improvement measures were taken. Nevertheless, the exhaust chimney penetrated the passenger cabin structure, necessitating measures. The passenger cabin side of the chimney was covered with soundproof material. In contrast, the gas turbine for power supply was always operated at high output, so silencers were installed on the exhaust side to prevent noise issues at stations. The basic structure of the vehicles was the same in the United States and Canada, but while Canada had a 7-car articulated trainset, the United States proposed shorter trainsets with either 1 or 3 middle bogies. Due to the articulated structure, it was a fixed formation, but it had a mechanism to increase or decrease middle bogies according to the application. The structure of the motive cars was distinctive, featuring multiple small gas turbines whose power was combined to drive the train. In the Canadian formation, there were a total of 4 gas turbines for driving and 2 for power supply, while the American formation had 6 for driving, 1 for power supply, and 1 electric motor. With a target of achieving speeds over 250 km per hour, shorter formations were more realistic in terms of performance. On the other hand, the American formation was equipped with an electric motor, as mentioned earlier, to accommodate underground station entry, and it ran slowly on underground sections using only the electric motor. Not only the power unit but also the body made of aluminum, and by applying aircraft methods for weight reduction, even in the Canadian formation, the output at wheel rim per weight was raised to twice that of diesel locomotive-hauled passenger trains with almost the same seating capacity. However, despite the lightweight structure, the Canadian formation was insufficient to achieve commercial speeds over 250 km per hour. Let's see how the differences between the two formations impacted performance. Due to a lack of data on air resistance and reduction ratio, these estimates are based on the characteristics of small cross-section bodies and the mechanical power transmission system of 2-axle gas turbine motor cars. This estimation assumes a weight of 100 tons with 6 engines producing 2,400 horsepower in the American formation, and the reduction ratio set so that the design point for engine operation speed is 210 km per hour. The compact ultra-lightweight body demonstrated its effect, boasting quite high acceleration performance for that time. When running on the uphill grade of the Takedo Shinkansen Sekigahara section, the balancing speed exceeding 200 km per hour overwhelmed the performance of the Series 0 EMUs. This indicates that United Aircraft Corporation's promotion of the train as an ultra-lightweight high-speed train had a valid foundation. In contrast, calculations for the Canadian 7-car articulated formation under the same conditions showed a significant performance decrease due to fewer engines and heavier formation. Achieving 240 km per hour on flat lines was the best it could do, and on a 10 per mile uphill grade, it could only reach 150 km per hour. This raised doubts about promoting it as a high-speed train exceeding 200 km per hour, leading to disputes with Canadian National Railways later on. In 1967, a high-speed test was conducted to confirm the performance and highlight the high-speed capability of the TurboTrain before commercial operation in the United States, setting a speed record of 274.9 km per hour. This became the world record for internal combustion vehicles at that time, surpassing not only the diesel vehicle speed records, which were capped around 200 km per hour, but also the world record for EMUs held by the Series 0 Shinkansen in Japan, showcasing the high-speed performance of gas turbine vehicles. The TurboTrain, which was welcomed with great expectations, began commercial operations in the United States in 1969 under the nickname Turbo Yankee Clipper, connecting New York and Boston over a distance of 370 kilometers in 3 hours and 39 minutes, with a maximum operating speed of 160 kilometers per hour. Since it did not run on dedicated new tracks, the track conditions were poor, and it was difficult to call it a high-speed railway in terms of speed. Additionally, as previously mentioned, it was equipped with a driving electric motor to accommodate the entry into New York's Grand Central Station, an underground station, and was fitted with current collection shoes to draw power from the third rail for underground operation. However, once commercial operations began, various problems emerged. The vibrations inside the train, particularly due to the special single-axle articulated structure and pendulum suspension bogies, were quite severe, resulting in very poor ride comfort evaluations. This issue was not prominent in the motive cars with two-axle bogies, indicating a problem with the single-axle bogie design. At the same time, the high-speed train Metroliner, which ran on electrified sections, also had a bad reputation due to significant vibrations. The Metroliner, with a conventional bogie high-speed train design, also faced issues due to high-speed operations on existing tracks. Frequent breakdowns were another issue, and the TurboTrain's timetable even included a note indicating that operations were dependent on the train's condition. High-speed rail operations on the east coast of the United States faced tough conditions from the start for both electric and turbine vehicles. Nevertheless, there was demand due to road congestion, and despite the uncertainty of when TurboTrains might be out of service, they maintained high occupancy rates. If track maintenance had been carried out, they might have performed reasonably well. However, the decline in passenger transport across the United States led to financial difficulties for railway companies, further exacerbating the situation. In 1971, all passenger transport businesses were transferred to Amtrak, funded by the federal government, including the TurboTrain. Thus, without fundamental improvements to both the vehicles and tracks, unstable operations continued until commercial operations ended in 1976, marking the end of its short lifespan. On the other hand, similar problems were prevalent in Canada. Due to the longer formation, speeds were slower, and although the journey between Montreal and Toronto was shortened by 1 hour compared to conventional diesel trains, it remained insufficient as a high-speed railway. Naturally, the expected operational speed was not achieved, and there was mutual blame between Canadian National Railways and the manufacturer, attributing issues to the vehicles, tracks, or operating methods. The design and manufacturing process was led mainly by aviation engineers, and the project proceeded without adequate coordination with railway operators, resulting in frequent issues right from the start of commercial operations. Most of the problems stemmed from the single-axle articulated structure, pendulum system, and inadequate cold and snow resistance in the middle bogie. The engines themselves did not seem to have significant issues. However, being in a cold region, unexpected problems arose, such as water droplets from washing freezing and damaging the compressor blades. This was unforeseen for the maintenance teams, who were only accustomed to handling diesel vehicles. Consequently, operations were suspended from 1971 to 1973, during which the vehicles were modified, and the formations were reconfigured. During this reconfiguration, the number of middle bogies was increased from 5 to 7, resulting in a 9-car formation. This led to a further decline in running performance, but as part of the vehicle improvement, the engines were replaced, increasing the output by 30% to 520 horsepower. The formation output became 2080 horsepower, aiming to compensate for the weight increase due to the additional 2 middle bogies. Let's look at the impact of these changes on the acceleration curves. This modification involved 120 changes, resulting in a maximum speed of 180 km per hour, a loaded weight of 260 tons, and an axle load of 17 tons on the driven wheels. There was an observed increase in weight, and the maximum speed was realistically controlled. The reduction ratio might have also changed, so the turbine design point speed was adjusted to 180 km per hour. The cleanliness of the skylights in the dome cars at both ends was also an issue. The roof, which was already prone to getting dirty, had gas turbine exhaust outlets nearby, exacerbating the problem. Even though gas turbine exhaust is relatively clean, a slight amount of smoke is produced when the output is rapidly increased. Consequently, the skylights were closed. Improvements were made to the pendulum suspension mechanism and exhaust silencers were added, leading to temporary failures, but operations as a special train began at the end of 1973. From the following year, the TurboTrain replaced one round trip of the existing limited express train, Rapido, and gradually increased the number of trips from that summer, with 3 formations being fully operational. Canadian National Railways promoted this as the second TurboTrain, even creating promotional brochures. While operations continued relatively smoothly, spare engines, drive axles with reduction mechanisms, and articulated bogies were always kept in the maintenance workshop at Montreal Station to prepare for breakdowns, with United Aircraft Corporation engineers maintaining them. However, like in the United States, railways struggled in Canada in terms of passenger transport, leading to the separation of the passenger division and its transfer to the state-owned Via Rail in 1978. Due to accidents and vehicle damage, commercial operations finally ended in 1982, and push-pull diesel trains took over, preventing the establishment of a high-speed rail culture in Canada. Japanese impressions of the turbotrains at that time were quite harsh. Several inspection teams were dispatched from Japan to investigate the development of high-speed rail in Europe and America. Naturally, railway experts and engineers participated, and there was significant interest in North American high-speed rail, as Japan was also developing gas turbine vehicles and researching further speed increases for the Shinkansen. Despite being an improved formation, the ride included vertical and horizontal swaying, as well as vibration, resulting in significant discomfort even though the commercial maximum speed was only 160 km per hour. Opinions about the noise from gas turbines in the dome cars, which were motive cars, varied. Some found it not problematic, while others found it quite noisy. The lead car, equipped with 2-axle bogies, offered a smooth ride. However, the gas turbine exhaust ducts ran through the passenger compartment, and during power application, passengers described the sound as akin to being inside a jet aircraft. During a Q&A session at the headquarters of Canadian National Railways, it was stated that the internal noise level was 75 decibel, and external noise was quieter than diesel locomotives. However, the inspection team felt that the internal noise level exceeded 85 decibel, and though they did not get a chance to hear the external noise, they imagined it to be quite noisy due to the design. In urban areas, it seemed they were careful with noise levels, as the engine output was significantly reduced near Montreal, leading to poor acceleration and restricted speeds. Although the single-axle articulated bogies with poor vibration performance left a bad impression, their pendulum mechanism was deemed quite effective. Nevertheless, brochures distributed to passengers included a note advising them to stay seated for 15 minutes after departure and before arrival. This was due to the lack of a mechanism to suppress pendulum action at low speeds, leading to significant swaying when passing through turnouts. Next, regarding the TurboTrain in the United States, observations from general travelers are also insightful. When boarding the dome car at the station, the initial impression was that it resembled a moving reception room, with a calm atmosphere and a sense of hospitality unmatched even by the Japanese Shinkansen. However, once the train began to move, it gradually started to sway, and as the speed increased, passengers were plagued by violent shaking and a machine gun-like banging noise from beneath the floor, leading to discomfort severe enough to make one question whether the vehicle would fall apart. Although they were in the lead motive car next to the exhaust chimney, there were no specific comments on engine noise, which might suggest that the loud banging noise from beneath the floor was due to poor track conditions rather than the high-pitched whine of the turbines. For Japanese people used to the dedicated high-speed new lines of the Shinkansen, it must have felt like an entirely different world. Even during expert inspections, the French TurboTrain was evaluated as almost passing, except for the large exterior noise, indicating that the high-speed rail technology in the United States at that time was still immature. The TurboTrain, which set the world speed record for commercial vehicles at the time, achieving 274.9 km per hour during high-speed tests, coincided with the overwhelming victory of the gas turbine car in the Indy 500-mile race, raising expectations for high-speed vehicles. In an attempt to bring the miracle that happened in aviation to railways, gas turbine drive systems gained attention in advanced railway countries. However, high-speed railways, dealing with the complex phenomena of vehicles and tracks and operating many trains, required comprehensive technology. Despite the engines being lightweight and high output, fully demonstrating their capabilities was not easy. In Canada, to replace the long-formation passenger limited express, a gangway door was installed at the front of the lead cars to couple two sets of 7-car articulated formations. However, this feature was never utilized in operations, and the structure's potential was never realized. This is similar to the 583 series sleeper EMUs in Japan, where the gangway doors on the lead cars were never put to practical use. Moreover, the oil shock caused fuel oil prices to skyrocket, and as the economy slowed, enthusiasm for gas turbines gradually waned, and the overall high-speed rail fervor in North America subsided. On the other hand, the French TurboTrain can be said to have been largely successful. Although the high-speed new lines were converted to electric operation, the TurboTrain for local lines survived even after the oil shock, built an export track record, and continued to operate for many years. Notably, it even entered the United States, where the UAC TurboTrain had withdrawn, and continued long-term operations.